Microscopy is really the study of visualizing small things. We want to be able to see things that we can't see with our naked eye to better understand how they work. Any way we can magnify an image is microscopy.
To me, microscopy is important because it allows me to see how a device, such as a microelectronic chip or a battery, can fail at the nanoscale, so that we can design new devices that perform better and last longer. My name is Tao Zhou. I am an assistant scientist at the Center for Nanoscale Materials of Argonne National Laboratory.
My name is Thomas Gage. I'm an assistant scientist at Argonne National Laboratory. Microscopy is critical for understanding how things work. Being able to see a real material, a real device at the nanoscale, micron scale, really shows you, are there defects? Are there effects of these boundaries that we didn't understand but are really critical to the functionality of a device? So things like batteries, things like transistors in your phone. These are all devices that operate truly at the atomic level. And without being able to understand how they work, we're never going to be able to improve or fix them.
Nowadays, with the best electron microscope we can buy, or if you do computational imaging, we have reached resolution that is a few times smaller than the size of an atom, so that you can really see the atoms with your own eyes.
A nanometer is a millionth of a millimeter. So now devices in your phone operate at the 2 nanometer level typically. So we're really approaching this kind of atomic kind of scale, which nanometer is quite similar to.
We just got a huge upgrade. Advanced Photon Source Upgrade Project is the way for us to get closer to the diffraction limit, and our beam gets brighter and more coherent. Now, by increasing the coherence of the light source, that allows the computational imaging methods to reach their full potential, basically.
So a microscope works by enlarging some kind of an image. The most simple example of this, I think, is a magnifying glass. You hold it over some kind of an object you're interested in, and it will bend the light that comes off of that, and that's able to enlarge the image as your eye sees it. More advanced microscopes are really just doing something like that, but many times and with a little bit more refinement. So a light microscope like you would use in a high school lab setting, it is quite similar, just more powerful lenses and more of them. An electron microscope used to see atoms and really at the frontier of the technique actually uses magnetic lenses. And that's because we need the magnets in order to bend the electrons in the same way that the glass lens in the magnifying glass would bend the light.
So I'm currently working with a full-field microscope. It works by placing an objective lens behind the sample that collects light that either passes through or scatters off the sample to form a magnified image on a camera. The optical microscope that we use in science class is also a full-field microscope. Now imagine this. With an optical microscope, you will need a light source, which is typically a light bulb, an LED. And the light source we have is a particle accelerator with a circumference of 1 kilometer. With optical microscope, you also need your eyepiece. The eyepiece in our case is a steel pipe that is 6 meters long and weighs a ton that rotates freely around the sample. Altogether, this microscope allows us to see tiny disturbances in the atomic matrix with a precision that is 100 times smaller than the size of an atom, using the principle of X-ray diffraction.
We have collaborators from chemistry and materials science, even collaborators from the new supercomputing facility. They all want to understand, really at the fundamental basic level, how their materials or systems work. At the end of the day, all things are made up of smaller things, and we need to understand how those work. And the best way to do that is to look at them.